In this video, I want to begin a journey, probably a 2 or 3 video journey in understanding right triangle geometry, how these trig functions are useful in solving triangles, and then also some word problems. But in this video, I'm going to keep it a little simpler. Let's just look at what these things are. What are these trig functions? And then in the next video, we'll actually be solving triangles using those trig functions. So here we go. Parts of a right triangle. Now the hypotenuse you already know is the longest side, but where is it located on the diagram on the right? It is across from the 90-degree angle. Right? Across from the 90-degree angle is the hypotenuse C. So across from the 90-degree angle is always the hypotenuse. Now, what about the opposite side? What are we talking about here? Well, this is a leg opposite an angle. Okay? So let's give an example. For example, side little a is opposite angle A. You see how here's angle A, and opposite that is side A. Okay, so the side is opposite the angle. So the adjacent side, what does the word adjacent mean? It means right next to. So the adjacent side is the leg next to an angle. So let me give you an example there. Example, B is adjacent to angle A. See, here's angle A, and side B is right next to it. See, across from it, that's the opposite side. So side A is opposite angle A, but leg B is said to be adjacent to A. Angle B has an adjacent leg also, right? Leg A is adjacent to angle B. It's right next to it. So the word adjacent means right next to it. Now, ratios of the sides of a right triangle are called trig ratios, trigonometric ratios. Now, ratios don't have units. They are simply a fraction, a ratio of two sides. So there are 3 ratios that I'm going to go through here today. There's actually 6 ratios, but I just wanted to keep it a little simpler, and let's stick to the primary ratios, which are sine, cosine, and tangent. So this first one is called sine of, and I put a Greek symbol, it's called theta. So you might want to write this down, theta. That is theta, sine of theta. So the sine of angle theta, and you see a picture over here. You see the theta right here? Let's write that in a little bit darker. So theta is down here. So we are going to imagine that we're sitting in angle theta. Sine of theta is always the ratio of two sides, and it is the opposite side over the hypotenuse. Hypotenuse. So sine is opposite over hypotenuse. So if you're sitting down here at this angle, we could give this angle, this side a letter, but what I'm saying here is we can also give the angle often a Greek letter, theta. So opposite would be over here, divided by hypotenuse. Okay, sine is opposite over hypotenuse. Now the next trig function we're going to go through is cosine. Cosine. Cosine of theta. Cosine of theta is a different trig ratio. It is adjacent over hypotenuse. So the leg that is next to the angle over the hypotenuse. So if we're sitting down here at theta, it would be adjacent divided by hypotenuse. So we would take the length of the adjacent side and divide by the length of the hypotenuse, and we would get a fraction or a decimal, and that's called cosine of theta. Now, what is the only combination we haven't done? Tangent. Tangent involves the two legs. That's something to just memorize. Tangent involves the two legs, and it's opposite divided by adjacent legs. So you always, if you're looking at theta, you always look at the legs, and the first one, the numerator in the fraction would be the opposite, and then the denominator would be the adjacent. So you take the two legs and you divide their values, however long they are, and that gives you a number, a fraction or a decimal. Now, a lot of students have a nifty way of remembering this. It's called SOH-CAH-TOA. You see how sine is opposite divided by hypotenuse. You see the SOH-CAH-TOA there? S-O-H. So, and then, what was the next one? Cosine. Cosine of theta is adjacent over hypotenuse. So there it is, C-A-H. And then the last one is tangent. Tangent of theta is opposite over adjacent. So once again, there's our T-O-A. So SOH-CAH-TOA. SOH-CAH-TOA. Sounds a little bit like a Native American term or something, but we just refer to this in trigonometry. SOH-CAH-TOA helps us remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So a lot of students write that on their paper immediately, or maybe draw this picture along with SOH-CAH-TOA so that they can figure that out later on. All right, you ready to get to some actual numbers now, I imagine, now that we've got some of the definition out of the way. So examples here. Find 3 trig ratios of the angle theta, so theta's down here, folks, in the following right triangle. In the following right triangle. So we have to imagine that we are sitting down here, okay? We are sitting at theta, and sine is, do you remember which one it is? Sine is opposite over hypotenuse. So if we're sitting right here, which leg is opposite? It would be the 3. So I'll go back over here and I'm going to write 3 on the top. That's my opposite divided by hypotenuse. The hypotenuse is the long side here, which is 5. So we can go back here and write a 5. So 3/5 or 0.6 if we were to divide that out. Okay, either way. So the ratio of the leg to the hypotenuse, the leg that is opposite of theta, is 3:5 all the time. Even in a 6:10 triangle, it would still be 3/5. Now, what about cosine? Cosine of theta. Cosine is adjacent over hypotenuse. You'll get these memorized once you work with them enough. So the adjacent leg would be right here. That's the one next to theta divided by the hypotenuse. So it would be 4/5, which is 0.8. Now, what about tangent? What about tangent? Remember, tangent involves just the legs, and it's the opposite leg divided by the adjacent leg. So that, in this case, would be, opposite is over here, 3 divided by the adjacent leg, 4. So 3/4, which we could also write as 0.75. 0.75. All right, let's look at this next one. Find the 3 trig functions for both A and B. So this time I'm not using the theta letter here. I'm just saying angle A and angle B. So the first part is all angle A. So I need you to imagine that you are sitting over here and you're going to be looking out across, right? So this one right here would be our opposite side, okay? And then this one over here is our adjacent, but we don't know the adjacent side. So the first order of business, I think, is maybe to figure out that adjacent leg. How could we do that? Well, we've learned Pythagorean's theorem, right? So 50 squared plus x squared equals the hypotenuse squared. Okay, so x squared equals 60 squared minus 50 squared. Now I've got the Desmos calculator all lined up off to the side here, so we can actually type this in. 60 squared minus 50 squared is 1100. And then we could put that entire thing under a square root, right, to solve it. So 1100 under the square root. Let me delete the rest of this. What a mess. And we get 33.167. So x equals 33.167. 33.167. So sometimes we use Pythagorean's theorem maybe to solve for that missing side. All right, so the sine of angle A, again, here's angle A. The sine is going to be opposite over hypotenuse. So what is the fraction? 50 over 60. What would be the cosine of angle A? Adjacent over hypotenuse. So that's going to be our 33.167 divided by 60. And then finally, tangent would be the opposite leg, which is 50 in this case, all over 33.167. Now, in part B here, where we're working with angle B, I'm going to have to erase some of this because now we're going to be sitting somewhere else. All right, as I'm looking at this question now, after I've erased everything, I realize it's labeled incorrectly. We need to label this here C, because C is always the right angle, and this will be B. So go ahead and correct that if you're following along here in some notes. So C should be the right angle. That doesn't affect our answer from the previous one, folks. All right, but it would affect our answer here next, because now we are going to imagine ourselves sitting down here. We are looking this way down from angle B for this second part over here. So let's write the ratios down. Sine of angle B would be the opposite. So this is no longer the adjacent side. Now this is the opposite. It's opposite of B. So sine of angle B would be 33.167 over the hypotenuse. Now the hypotenuse doesn't change here, folks. It's still the long side, which is 60. Now the leg that is next to angle B, which one is that? Here's angle B. What's next to it? The 50 this time. So this would be 50 over 60. And then tangent is going to be the opposite, which is 33.167 over 60. Do you notice anything interesting here? This might be a great observation you could make right now. Do you notice anything? Cosine of angle B is equal to the sine of angle A. That's kind of neat. The sine of angle B is equal to the cosine of angle A. All right, I made a goof here. Do you see what I did? This shouldn't have been 60. This should be over 50. So make sure you get that corrected. If you're following along right here, this should have been 50 because, silly me, I'm supposed to use legs, right? So tangent is the opposite over the adjacent leg. So that should be 50. Now you can see that these two are reciprocals of one another. If you flip it over, they are equal right there. So we found three trig functions for both of the angles, both angle A and angle B. Okay, let's continue on now to actually find some trig ratios given one of them. So if I know that the sine is 2/3, remember sine is opposite over hypotenuse. So if the opposite is 2 and the hypotenuse is 3, what are the other trig ratios here? Well, let's set up a triangle, folks. Let's set up a triangle, okay? So here's our theta. Opposite is 2, and hypotenuse is 3. So how could we figure out that other leg? Let's use the Pythagorean theorem. So Pythagorean theorem says that 2 squared plus b squared equals 3 squared. So b squared equals 9 minus 4. B squared equals the square root of 5. I'm sorry, b equals the square root of 5 when you square root both sides. All right, I know I did that quickly, but you're probably really good at the Pythagorean theorem by now. So this would be radical 5. Just write it radical 5. So if we are sitting down here at this angle, this is our perspective. That's what I mean by that. That's our theta down there. Our cosine ratio would be adjacent over hypotenuse, and that's going to be radical 5 over 3. Whereas tangent would be the opposite, which we already said was 2, over the adjacent. Now we just solved for that, right? So that would be 2 over radical 5. Now if your teacher wants you to rationalize that, you multiply by radical 5 over radical 5. We get 2 radical 5 over the square root of 25, which is 5. So either answers, in my opinion, would be great, right here or right here. Okay, let's continue on. Another triangle here. Sine is radical 5 over 4. All right, well, let's draw a picture. That always helps, right? Here's our theta right here. So that's the perspective, okay? So the opposite is radical 5, and the hypotenuse is 4. So once again, we need to solve for this missing leg down here, because after all, the 90-degree has to be right there. Okay, so how do we do that? Pythagorean theorem. So let's do that. We would have radical 5 squared plus b squared equals 4 squared. So this would be b squared is 16 minus 5, so b equals the square root of 11. So this equals the square root of 11 down here. So it does say find exact values, so that's why I'm not using any decimals here. So I want to keep it in terms of a radical. So here we go. The sine of theta is radical 5 over 4. Cosine would be adjacent. So what leg is next to our theta? That's that radical 11 that we just found. So radical 11 over, and the hypotenuse is 4. And then tangent is opposite over adjacent. Now once again, we don't like to have radicals in the denominator, so we have this process called rationalizing the denominator. I've made a couple videos about it because it is an important skill, and a lot of students have some troubles with that, but that's okay. I'm pretty thrilled if a student writes this, but you can also simplify it to be that expression right there, radical 55 over 11. Okay, let's do one more example where we're solving for the different trig functions. So let's draw our triangle, okay? So this will be our beta down here. That's the Greek letter beta we sometimes use as an angle. Our right angle will be right here. Cosine is 0.32. Now that's over 1. So it is a ratio. So the adjacent would be 0.32, and the hypotenuse would be 1. So we need to figure out that other leg, folks, again. So Pythagorean theorem will do it. 0.32 squared plus a squared is 1 squared. So a is going to be the square root of 1 minus 0.32 squared. So I think I'll go to my calculator on that one, and we'll go ahead and type that in. 1 minus 0.32 squared. And the answer is A is 0.95. I'll round it to hundredths since the original problem was hundredths also. Okay, so now we can write our other trig functions. Sine of beta would be the opposite. We just figured out that the opposite is 0.95. So it's 0.95 to 1, which is just 0.95. And then tangent beta would be 0.95 divided by 0.32. So I could even take that then. Let me get outside here. I could divide that number, divide by 0.32. So Just want to make sure I was getting the fraction correct there. So this would be 2.96. 2.96 is how the value for tangent. All right, so I have a couple questions here for you that I think sort of hint at what we're going to talk about in that next video, in the next section. But if the sine of angle A, here's angle A, okay, if the sine is 1 over 2, that means we have a 1 to 2 relationship between the opposite and the hypotenuse. What does that mean is always true about the leg BC. So BC is right here, and the hypotenuse AB. Well, let's fill in the values. So if the sine is 1/2, sine of angle A, so remember I always draw like a little guy here because again, we're looking from that perspective, right? We're looking out over here. So this A is opposite. So over here, this is our opposite, and then here's our hypotenuse, of course, which is the longest side. So we have a 1 to 2 relationship between this leg and the hypotenuse. So what is always true? The hypotenuse is twice as big as the short leg there. Short leg, or the leg that's opposite that angle. Short leg or opposite angle A. So side A is always half as big as the hypotenuse, or you could say the hypotenuse is twice as big as the short leg. So that's kind of cool. So it doesn't matter if it's a triangle where the hypotenuse is 8, how big would that short leg be? It would be half as big because the hypotenuse needs to be twice as big. So if this angle A is the same value as this angle A, if these are similar triangles, then we'd have an 8 to 4 or a 4 to 8 relationship between that leg and the hypotenuse. All right, moving on. If the sine of angle A is 1/2 and the hypotenuse is 8, this was the question that I just answered. So if we have a 1 to 2 relationship between the leg that's opposite A and the hypotenuse, 1 to 2 relationship, and if we know the hypotenuse is 8, how big does the short leg there have to be? This would be 4 centimeters long. It would be 4 centimeters long since the leg to hypotenuse have a 1 to 2 proportion, right? There's those proportions that we've solved before in our math class. So these trig ratios will allow us to actually solve for sides of the triangle if we have an angle. And we're going to learn how to do that in the next section using a calculator and everything. It's really pretty easy once you set it up. So this video really just meant to give you an introduction to the three main trig functions and how to find their ratios and how to find their decimal values, and then we'll put them to work in the next video. All right, good luck, and until next time.